Can everybody hear me? Is it okay? Great. So the first thing that I wanted to review was about positive output 2D field theories. So we can't have a talk without talking about Lurie's paper. So I'll start with that. So A is a smooth DGA. So this is a definition over a field of characteristic 0. If A is perfect as an AA bimodule.
What does that mean?
Next sentence.
What?
As a next sentence.
Okay.
So, and by perfect as an AA bimodule, that means that so A is, i.e., A is in the smallest triangulated category. So idempotent. So so.
I'm sorry. That sentence doesn't seem to have a verb.
Are you missing is a?
Yeah.
What?
A is a?
Yeah.
Yes.
A is a smooth, right, definition.
Wonderful.
A is a smooth DGA if, over a field of characteristics 0, if A is perfect as an AA bimodule, which means that A is in the smallest idempotent closed triangulated category of AA bimodules generated by A tensor A op. Okay. So by idempotent closed, I just mean that you don't want to just have so triangulated means that you include the mapping cones of morphisms. So that's what it means to take the triangulated closure. And idempotent closed also means that you want to pass to direct summons. So if you have something that's a direct summon, you also want to allow you have something that's a sum. You want to allow each of the direct summons in there.
What?
So if you have like m plus n, you also want to allow m and n in your category.
So this A has an AA bimodule, which is the smallest.
Right. So so if A is an ordinary ring, this just means that. So let's say A is a commutative ring, then this is just A tensor A, and this would just mean that A as a module over A tensor A has a finite projective resolution.
Or free.
Well, no, that the passing to idempotent closed, you won't have a finite free one maybe, but you'll have, if you pass to idempotent closure, then you have a finite projective one.
So the statement you forget about completely about the differential. Yeah? That's not depend on the equation.
I mean, A is A is a DGA, so you have to also this is
with differential, everything with differential.
Yeah, with differential, yeah.
Sorry.
AA differential.
So you're saying, given a DGA over a field of characteristic 0, we'll say it's smooth if it's perfect over an AA.
Right. That's right. That's right. Okay.
So this adds a differential AA bimodule.
Right. Yeah. 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 Okay. So one thing to notice is that. So I guess I'll leave that definition up here.
The Duram complex of a compact manifold is not smooth.
That's right. The Duram complex won't be smooth. Exactly. Unless you're, yeah, of a compact manifold, fine. Okay.
That was a serious question. I wasn't.
No, it's shocking.
Okay, so one thing to notice is that if M is perfect,
What's an example?
well, any smooth commutative ring in degree 0 will satisfy that. So you have like a polynomial ring. Smooth is in like the variety is smooth. Then that'll satisfy that.
Affine variety.
Yeah, you have a smooth affine variety.
A smooth affine variety.
That'll satisfy that condition. Yeah. So if you notice, so if M is perfect, then so this is any M which is perfect as an AA bimodule, then you have the following isomorphism, which is that. So I'll denote A tensor A out by AE from now on. So this is by definition.
What's that little thing you wrote out with the A? I can't read.
This one?
Yeah.
An E. I'll always denote A tensor A out by AE just to save space.
Oh, no, okay. Developing.
Yeah. So this is by definition the Hochschild homology with coefficients in M, but there's always an isomorphism between this and Hom over AE between the following two modules. So you always get an isom.
You have Hochschild somewhere in there?
Yeah, this is Hochschild right here.
Okay.
And so this is if M is perfect. And so in particular, if M is A, what you get is you get an element in the Hom complex between this bimodule and that bimodule. And so, right, so what I want to say is, so Hochschild homology with coefficients in A, there's also a circle action given by the Kahn operator. And the homotopy fixed points of that circle action. Yeah.
I mean, at some point we derive everything.
Everything is derived. Whenever I say anything, it's derived. Yeah, everything is Hom. This is derived. This is derived. I don't want to do it because I'll have to do it everywhere where I write something. So just everything. Anytime there's a tensor product, it's the derived tensor product.
You derive where you don't have
If you write star,
Star where?
you have the star there.
Here?
No, lower star and HH.
Lower star. Oh. Oh yeah. So the complex. Yeah, the Hochschild. Well, if you want, you'd have to take homology of this would still have to be derived if you wanted this to be the Hochschild homology. This would still have to be the derived tensor product. But this is in the these are AE bimodules, and there's this is in the derived category, these are equivalent.
No, but he has a fair point. You could say let everything be derived, but then you sort of have to be consistent, either at the chain complex level or the homology level.
Right.
So you've mixed the two levels.
No, this is a chain level. This is I'm saying in the derived category.
He wants to use a C instead of an H.
Yeah, but
He wants to use a C.
the left-hand side, when you say that's derived, what do you mean over there?
Well, the derived tensor product, meaning you have to replace this by
By the chain complex.
by a co-5, you have to take a resolution. Okay, so you have this.
And over there, you mean the chain complexes for the Hom.
Yeah, everything, right.
Everything is a chain complex.
Everything is a chain complex. Okay, so if it's not a chain complex, I guess I can underline it, or I don't know if you're worried. So So you have the, okay, I can, well, anyway, so you have the negative, so this gives a circle action, and negative cyclic homology is the homotopy invariance. So this is a definition. The negative cyclic homology is the homotopy invariance of this circle action. And so I'll make, now this is all building towards a definition, which is that you say that we have a definition, which is that we say that A has an n Calabi-Yau structure. Yeah?
So U is like a generated a circle?
Yeah, right. Is the
B is the what is little b?
little b was the differential here. Yeah. So yeah, so it's the ordinary differential plus U times the the homotopy invariance of that circle action. So we say that A has an n Calabi-Yau structure if there's an element of negative cyclic homology such that, the other thing to notice is that there's a map pi lower star from the negative cyclic homology of A to the Hochschild homology. And so we say that, so if there's an element of the negative cyclic homology such that, so I should call this element alpha, such that pi lower star of alpha induces an isomorphism. So if you're really unhappy about the derived category, then so we'll say a quasi-isomorphism from Hom AE to, so this our class alpha will have some degree, so that will mean that the map will have a shift. So you'll have a quasi-isomorphism like this. Pi star is this, so you always have a, so that you can't, this doesn't, so Hochschild homology doesn't sit as a subcomplex of this, but you always have a map down to Hochschild homology. So there's always a map like that. And so you have an alpha in here, so the pi lower star of it induces this kind of quasi-isomorphism. So that's the definition.
The map is just setting U equal to 0?
Right. Well, right. It's just taking the part where you yeah, exactly. Yeah.
This negative cyclic homology, can you explain what you wrote?
This?
Yeah, just that expression.
This is, so what you do is you take the Hochschild complex, you adjoin this formal variable U, which is supposed to represent cohomology of BS1, the generator, and then you have this differential here, which is B, which I was just denoting for it's the usual notation for the ordinary differential in Hochschild homology, and UB, so you twist it by this. It's kind of like a Cartan model, a Cartan model for the invariance, and this is the definition.
If the smooth Laurent complex of the closed manifold would satisfy just this?
No, so the Durand, because it doesn't satisfy that. So
No, it doesn't satisfy that, but would it just satisfy this by itself?
No, they're just for compact guys. There's a kind of a different definition you want to use, which is you don't want to use the negative cyclic homology. What you want to use is the ordinary cyclic homology.
It's probably better to say you should use chains on the loop space, guys.
Yeah.
If you use chains on the base loop space.
What?
Chains on the base loop space.
Satisfies
All of this. So it's the dual version.
Right.
Satisfies the second thing.
All of the axes.
Right. The problem is that the Hochschild homology of the de Rham complex, at least if you're simply connected, is the cohomology. So you kind of there's a dual notion that you need for that situation. But this is
So the free loops, the base loop space satisfies this.
the base loop space, right? The base loop space satisfies this
Not that.
and that.
Huh?
The base loop space satisfies both. Of a smooth manifold satisfies both conditions. I mean, it satisfies this, and then I mean you can't make sense of this. This doesn't make sense for the de Rham complex because you need that M is perfect, which means to establish this isomorphism. And if it's not, and in that case we've already studied, so it's not perfect, so you don't have this isomorphism, so you can't even talk about whether you have a map like that or not. Does that make sense? Right. So.
Such that Pylos are
Yeah. So, sorry for my writing. What are we trying to decipher here?
How does Pylos alpha induce a map?
So I'm saying alpha. Oh, because remember, so Pylo or star is in here, and then we have this isomorphism, where you put A, right? So then you'd get a map from this guy to that guy. And this class can have some degree, so you won't get a map directly, you'll get a map to the shift. What?
In the inside home, is there some
Where?
in the inside, in the second home there. There's a home AE, and
The inside
for
home.
this you need another AE there.
Oh, here. Yeah.
And if you are there, I mean, probably the B also has a shift here. I mean, here probably is not confusing. The B
No,
map-
this B.
The B map shifts degree is.
Right. That's to make this a complex. So wait. What? Yeah, I'm missing B. Oh, B. Yeah. If you right. So B shifts degrees. B is it's another differential with squares to 0. So it generates a circle action.
And then if you go for the loop space, so I mean, do you mean the definition of smooth that anything which is quasi-isomorphic to something
Right.
satisfying this is also inside?
Right. Because it's you're passing to the homotopy cat. When you say the triangulated category, you pass to the homotopy category. So you include things which, when you take this triangulated category generated by, you also take things which are quasi-isomorphic to the things that are in there. Say that again. No, the de Rham complex. Well, if you think about like on S2, the de Rham complex is quasi-isomorphic to R joins X mod X squared, and that's not going to have a finite resolution, if that makes sense. Yeah. Okay. So the theorem, which
When Kevin said the base loop space satisfies perfectly, you mean the homology of the base loop space?
no. As a DGA, that satisfies this condition. That satisfies this.
Forms.
Forms don't satisfy this condition.
No, the forms. Basically, what aspect of the free loop space satisfies that definition?
Chains on the base loop space.
Chains.
Right, on the base loop space. Yeah.
So it's a non-commutative algebra.
Right.
Would change in the base loop space of a dimension M manifold. Is that M the same as that M?
M.
And
N. Yeah. That would be the same as this N. Yeah. Okay.
Chains on the base loop space of a closed manifold.
Well, chains on the base, actually chains on, for that condition you need it to be a manifold, or at least satisfy Poincare duality. For that condition you can have any finite CW complex. So then the theorem, which is not mine, which is Lurie and Kontsevich, I guess. Well, let's just say the only place it's written down is by Lurie. So given such a structure, we get a 2D field theory, but we require the so over the prop where the number of outputs. Oh, okay. I can write bigger. So the number of outputs, n, is bigger than 0. So you can't close up your surfaces, but there's earlier work by Costello where you had the opposite. These two definitions of Calabi-Yau are in some sense dual, because the earlier work you had to have a certain number of inputs. You had to have at least one input, and now here you have to have a certain number of outputs with this definition. So the de Rham complex would satisfy this other definition where you have to have at least one input. That's okay. So to write that down. M, right. So this is the moduli space of surfaces with n inputs and n outputs, right? So great. So the example.
Can you say the degrees?
The degrees of
operators.
Yeah, I mean the degrees, right? The degrees. I mean, it's some formula in terms of that. It's like in string topology, exactly. Yeah. So the example for everyone else's benefit is string topology, although it's only kind of the defined part of string topology. String topology is potentially a richer structure than this, but so if M is a compact oriented manifold. Oh, if M is a compact oriented manifold, then we want A equals to chains on the base loop space of M with coefficients in Q. And therefore, the Hochschild homology of A is isomorphic to the homology of the loop space of M. And you have a map from the homology of M to the homology of the loop space of M. And what you want is the class in Hochschild homology that you want is the fundamental class. Or the image of the fundamental class is equal to pi lower star of alpha. Okay, so now we have this was all kind of background.
So this is a chain level theory.
Right. This is a chain level theory, but it doesn't. It's only kind of over this open moduli space where you have.
Yeah.
Yeah. Cyclic homology? Yeah, you can lift this. I mean, the thing that's you can lift the point is that you can lift that to cyclic homology, but it's not. This is a kind of the easiest map to describe. I'm just saying what the image is under pi lower star. So, okay. So here's the motivating question for what I want to talk about. Which is, can we deform? So this is going to be formulated slightly vaguely right now, but I'll come to a more precise formulation in a second, which is, can we deform chains on the base loop space of M so that we can obtain a field theory over with no restrictions on N or M. So that's the vague question, and so we're going to make this question more precise by restricting the M.
Yeah. Oh, the small m.
Yeah, the M, the number of outputs. So.
Can you just say one word now about what you mean by deform?
Right. Well, why don't I just say that? Oh, deform meaning put a parameter, you know, a t variable, and then pass. So you have a deformation.
Context of perfect whatever and so on.
Right. Right. Well, for this guy, you know, this.
Oh, that guy.
Right. So you have a deformation. So you put a parameter t, and then you pass to the generic fiber, and then the question is that going to be fully dualizable in an appropriate sense? So in order to do that, you
put a parameter t for what structure? The ring structure?
Well, yeah, it's going to be a deformation of not DGAs but curved DGAs, and you're going to consider the module categories over those, and right. So I'll make it more precise now. But we're going to have to restrict M to a particularly nice class in terms of its rational homotopy type. So
this very theorem is sort of equivariant as well.
what is it?
The circle actions on the boundaries.
Ooh,
With the B operators.
I don't know what that means.
Okay.
Sorry. You get meaning you can always take cyclic homology. Is that what you mean? You can always take cyclic homology, and that gives you some kind of, that's going to have some structure to it. Right. So you can get some structure. Yeah. So we're going to say another definition. The rational homotopy type of M is pure if cochains on the manifold, on your manifold has, with coefficients in Q, has a model of the following form. So well, I should probably not make these the same as the M and N, or people are going to yell at me. OK, so right, but the differential. So you want the differential of the DEIs to be, some Fi, where the degree of Fi is bigger than 2, bigger than or equal to 2, and the degree of the differential of the Uj is equal to 0. So it's a very specific.
That degree, you mean the monomial degree or the?
Right, the monomial. So I want it to be minimal. I don't want it to have.
Monomial degree.
Monomial degree, right.
And it's in the U's, or can it be?
And
mixed?
I should say that I want I also want M to be simply connected here. Yeah. Because I want to apply rational homotype.
Fi in the algebra is generated by the U's or not?
Right. Generated by the U's. Right. Fi of the U's.
Fi is in the U's.
Fi is in the U's. Right. So
Don't write that either, though.
Yeah. Okay. So.
Those spaces are complicated, even if you have one epsilon.
Yeah. Well, so since we want M to be a manifold, or at least a Poincare duality space, then you.
Oh, you gotta have
Yeah. So it's not going to be. You're going to have more. But yeah. So the homology. So if you work a little bit of rational homotopy theory, you realize that the homology of the chains on the base loop space is a Clifford algebra over these Q of V. So over it's a Clifford algebra. So these variables are cojoule dual to these. So it's a Clifford algebra over this polynomial ring, and the higher you can actually apply perturbation lemma, and the higher operations.
What are the EIs?
What?
Sorry. Can you read the sentence again? What's EIs?
EIs?
Oh,
Oh, these are cojoule dual to. So the chains on the base loop. So since I said we wanted to also restrict M to be simply connected, then this guy is cojoule dual to that. So these variables. So it's kind of like an even odd dual, fermion, whatever they call it. These variables here are cojoule dual to those. Right. The quadratic form is given. So remember, if you study rational homotopy theory, this guy is the Chevalier. So that's going to be determined. This is the Chevalier complex over the Lie algebra, which is pi lower star of so you have this kind of Lie algebra, right? Which has a Whitehead bracket. So this is a Lie algebra, but if you notice that it's trivial on the even part, and it's but the only interesting data here is on the odd part is a map from the odd to the odd tensor odd to even, and that's actually, but it's going to be symmetric because it's a you have the only non-trivial bracket goes from G odd tensor G odd to G even. And this is symmetric because it's odd. Right, so that's where the Clifford algebra structure comes from. So what you find out is that the higher, so when you perform your perturbation lemma, the higher operations are linear. So the higher operations have the property that Mn of W alpha 1 so where W, if W is in this is for n bigger than or equal to 3, V1, Vk, and that tells you that these functions W satisfies the Maurer-Cartan equation in Hochschild cohomology of so you can WT satisfies it in this guy. So this gadget controls the deformation theory of A, and so WT satisfies the Maurer-Cartan equation, which means that you get a deformation. So you get a curve, what's called a curve deformation.
What are the W's? Are you?
Yeah.
Can you? The sentence you said that you changed the quantifiers twice when you said it twice, and then I lost it.
Okay.
If you have if WT or
so W. So I want to make it clear that W is in here. W is in the.
W is in there.
Then WT satisfies the Maurer-Cartan equation here.
WT.
W times T.
W times T.
So you join a form. This is where we were talking about adjoining the formal variable, and you get a curve, what's called a curve deformation of your algebra A.
Okay.
This controls the deformation theory. So it's a deformation.
No, but it's the English sentence I'm not hearing. How
Yeah.
it's quantified. There exists W if any W.
For any W, right? I'm saying.
Any W in there.
Yeah.
And then erase that implies and put a comma. Then you'll have.
For any W in there. The border.
No, I mean, okay. Then we have this. Fine. You can say it this way, or I wanted to make it so that you can have W's in other parts of.
It doesn't matter where you're going, but this just gets simplification.
Yeah. Does this make sense?
Any W in there, then it satisfies the Maurer-Cartan equation.
Right.
Relative to what structure are you thinking about?
Well, there's the canonical,
oh, you mean the Gersten-Haber?
Right.
For the deformation. The
deformation theory thing. Right.
Why is that?
Well, it's just an equation, right? So you can.
No, but
it's so the things.
Are non-trivial. They're not non-linear, for example.
Right. That's where these conditions come in. This. So more. So this is.
What are those higher products that you said were zero?
When you do the perturbation lemma, so you can obtain a model, which is your on this guy, which is your Clifford algebra, and then you have these higher, but it's not formal, so you have these higher operations, and what happens is that. What? Oh, these are just anything, anything in the, so these MNs take n inputs and spit out something. Yeah.
I guess there's two questions.
Yeah.
Firstly, so these higher operations, is that equal to 0 or only equal to 0 when one of the inputs is this particular choice?
Well, if
for W,
right for if you have a right.
In general, that there are.
Right. So if you have there are higher operations. But I'm saying that the fact that these guys satisfy this equation is it says that they're in the center of you can tell they're so on homology the first equation, what is HH0 of an algebra? It's the center, right? So these things are clearly in the center, but they're more in the center. They're in kind of this homotopy center, if you want. So they satisfy this equation. That's the idea. Does that make sense?
I understand the statement. I understand what you're stating.
Okay. Well, I can try to say more if you want.
No, come on.
Okay. So I was going to give an example which might be familiar, although so. That's not good. Okay. So.
One question. I mean, so if you write H star, you really, in this case, you really mean homology. I mean, it's not a shaking thing.
Say it again.
I mean, here if you write H star of the.
Right, the homology.
That is the honest homology.
Yeah. No, the homology. I'm saying the homology is a Clifford algebra.
Then how do you get these omega t inside this shaking?
Omega t. These live in here.
Why?
Because Hochschild 0. If you start writing this complex, Hochschild 0 of the first part of Hochschild.
At one point you took homology.
Right.
You specified an element inside of the homology, and he's asking. But now you're saying something at the chain level.
Right. I'm saying you get.
Or any class representing this homology?
No. I'm saying pass to. Pass to a minimal model. Like apply the perturbation lemma, and you have this. You can. Does that make sense?
So you're saying apply the perturbation lemma that.
So this is so.
What structure?
To you can write down a model for chains on the base loop space. So to chains on the base loop space, I'm saying you apply this, and then.
So you mean the associative algebra structure there.
Right.
You can transport that to the homology, which
Right.
is a different algebra. Look at the higher terms.
Right.
They vanish for 3 and above.
Right.
And therefore it satisfies something.
Right.
With deformation.
Right.
That's the statement you're making.
That's the statement I'm making. Yeah. Yes. You have. Right.
That statement is not why it's true. That's fine.
So the example that I wanted to do. Can I say that again?
V1 DK. Are these spherical generators?
Are they what?
Clifford algebra.
V1 VK, yes.
Are these spherical generators?
Spherical. Oh, do they correspond to. They correspond to they correspond to elements in this. Right, they correspond to elements in here. Yeah.
So how do you lift them to chain everything? Then you started to explain something and then you were interrupted.
Oh.
So you wanted to explain how you get from W, which is a commodity class, something.
Oh, right. So I'm saying you can write an A infinity algebra. That's what I'm trying to say. There's an A infinity algebra on this homology. So that has a perfectly good Hochschild, complex. And I'm saying that this condition implies that in the Hochschild cochains, the first part even for an A infinity, whatever kind of A infinity algebra or whatever kind of gadget you have, Hochschild 0 is right. Hochschild 0 is just Hom from the ground field into A. So it's an actual. I'm saying your underlying vector space will now be the homology, but with higher operations. It's an A infinity algebra. Does that answer the question? So this A now has as a vector space this, but with higher operations. Yeah. So maybe if I do an example, it'll be So I'm saying if you have kind of just the most basic example, which is an exterior algebra. Did I? Yeah.
But in the natural set of examples, the two compact Lie groups, H contained in G and G mod H, that homogeneous space?
Yeah, that would be a great. That's more complicated.
Okay.
Right. Yeah, that's a very natural.
Set of
That's
examples
for those. That's a very interesting set of examples for those. Yeah. Yeah. So if you have an exterior algebra, then chains on, well then, yeah, is actually quasi-isomorphic to this polynomial ring. And, right. And so what you can consider is, and then you can consider any function in here, and what you get essentially, so you can associate it to a category which is the category of matrix factorizations. So this is kind of the basic. There's some minor subtlety with gradings, but this is just this for motivation. Yeah, the subtlety, if you're, it's not the gradings aren't such a big deal. So you have this category here, and
two vector spaces and two maps between them or something. What is that? What does that MF mean?
Right. So the MF means you have projective modules. So it's two maps like this, where you have D0 and D1, such that D0 composed with D1 equals D1 composed with D0, which is equal to multiplication by the identity times W. So multiplication by W.
Wrote D1, D0.
D0. So you can compose either way, and you get multiplication by W. So it's a matrix, because the reason it's called a matrix, it's a factorization of W, because if these were free, then that's exactly what you would get. So then the theorem. So if I want to explain anything about what I did, I should cut to the chase. So basically, the theorem is. Here is that the following are equivalent. W has isolated singularities.
What's W?
W is this element that I was talking about. W. The Hochschild cohomology is finite dimensional. And 3, MF of Q V1 VK, comma W is smooth, proper, and Calabi-Yau. So the reason that I'm emphasizing this is that the condition that W having isolated singularities can be rephrased as the Hochschild cohomology being finite dimensional. In fact, if you compute what the Hochschild cohomology of this thing is, it's so HH0 of MF is equal to the Jacobian ring of W.
But why is this thing a ring? It didn't quite define it.
Which thing?
MF.
Well, so it's the category of modules. It's the category of these. It's this, so you have to say, so these are the objects of the category, right? And then you have to define what you mean to be morphisms between them, but it's just kind of the obvious thing. And then
That category is equivalent to a category of one object, or you just
you can make it equivalent. There's a generator for there's always a generator for this category, and indeed, yeah.
So then this third thing makes sense.
Right. Well, yeah.
What does proper mean? It's a new word.
Proper. You can think that it means that all the Homs in here are finite dimensional.
All the Homs and where?
In this category are finite dimensional.
Oh.
Yeah. So if you have a DGA, proper would mean that the cohomology of that DGA is finite dimensional. Okay, so you can rephrase it in this way. So what I was going to say is that here you get the Jacobian ring, and the rest of Hochschild cohomology is a finite is a coherent module over this guy. So if this is finite, so having isolated singularities means this is finite, and then everything else is automatically finite dimensional. So you can rephrase this. You can rephrase this as having isolated singularities as this being finite dimensional. So that's kind of useful in our non-commutative.
1B, W has a single isolated singularity.
Here, I mean, so no, W can in this with matrix factorizations, W can have, it just has to have isolated singularities.
Disjoint direct sum.
Right, but it'll be finite.
Rings.
Yeah, it's just right. Yeah, exactly. So we can rephrase, and let me see. So I'll tell you how I define. So there's a couple of ways you can define the category of matrix factorizations in our setting. Right. So I should mention that there's a classical theorem of Orlov which will motivate the easiest way to define it, which is that you can take coherent sheaves on Q adjoins V1 through Vk modulo W. And you can divide out by the perfect and this is called the category of singularities. So coherent just means finitely generated, and this means perfect in the sense that we were talking about earlier. And so this category is equivalent to the category of matrix factorizations via some you take the co-kernel. If you take the co-kernel of D naught, you get a coherent sheaf here, and that's the equivalence. So here we're going to define. So we have a category pre-MF of A comma W, which is equal to A adjoins E. So now A, I'm saying A is like these non-commutative examples I mentioned earlier. So you have pre-MF, which is this category of modules, but those which are perfect over A. So you notice that if you had a coherent sheaf, well, right. So if you have a coherent sheaf on this guy, it's perfect over the polynomial ring, because any finite dimensional module is perfect over the polynomial ring, and that's Hilbert's theorem. And the theorem, and then we want to quotient out by those. So we define MF of, this is another definition, is equal to the pre-MF of AW modulo the perfect so you have this definition, which is exactly that. And the theorem for these guys is that the Hochschild cohomology
W is an element in A, right?
W is
In this definition here.
W is in here.
Yeah. In
Right.
this definition, W is just any element of A.
No, W is one of these inside this polynomial.
This seems to be a definition with the symbol A in it. Okay, go ahead. Go ahead.
Right. A was this.
A is that A. Okay,
Yeah.
A is that.
Yeah, as above. So Hochschild cohomology of MF with AW is finite dimensional. Definitely if MF of AW is smooth, proper, and Calabi-Yau. So this doesn't seem like much of an advancement, but because obviously if all this is true, then your Hochschild, this is a necessary requirement, but it's something that can be checked. It can actually be computed. And so an example, if M is CPN, then you have Q adjoins V. So your model for your pure model looks like this. Right? And so chains on the base loop space is like this with one higher product. So so all the higher products are linear over this subalgebra, this A infinity subalgebra, and you have a higher product like this, and that determines all the higher operations. And if you consider W equals to V to the D for any D, you can check that it satisfies this condition, and therefore that you actually get. This is just an example of something you get. You can check that you get for every D you get a TQFT, which has some interpretation in terms of Floer theory and the Fukaya category. But since I have 1 minute, I'll just ask for more questions instead of going into that. Yeah?
You didn't explain how these deformations somehow gives rise to the TQFT.
Right.
Repeat the question. I couldn't hear.
He asked, can you explain how this deformation gives rise to a TQFT? Well, so it satisfies now all the conditions to be fully dualizable, not just, So it was missing. You were missing before. You were missing this condition, and now you have it, and then you get the TQFT. Yeah.
I would imagine if you wanted to reason with the fundamental chain of moduli disks to compute such a guy. Is that what you holomorphic disks and the symplectic manifold?
Repeat the question.
Yeah, please. It's also great for the video to have the question repeated.
OK, can you repeat the question to me, and then I'll try to repeat it.
You mentioned Floer theory, so I would guess there'd be something to do with the fundamental chain of moduli holomorphic disks and the symplectic manifold, giving you more cochain.
So the question is if the Floer theoretic interpretation has something to do with the fundamental chain of the moduli space of holomorphic disks. So the relationship between Floer theory that I have in mind is that if you have a cotangent bundle of a compact oriented manifold, you have some compactification of that cotangent that gives you a deformation of the Fukaya category. And so for CPN, there is some reasonable compactification, and that I can match those up with these deformations. That's
So like by counting disks ending on the zero section going off here.
right, exactly, yeah.
So you're saying your deformation has an interpretation in terms of this compactification of the tangent bundle of CPN.
Exactly, yeah, you can.
Defined by algebraic geometry.
Right, yeah, exactly. But maybe I was too ambitious with my talk after all. Any other questions? Or?
I had a comment. Graham Siegel once told me many years ago this fascinating thing, and I like to want to bring it up at this conference, that these field theories have the property that whatever algebraic structure they have, they deform themselves. Because suppose you have some algebraic structure, a bunch of Riemann surfaces giving a bunch of structures, right? Then you can just take all those Riemann surfaces and find that structure, and you can just stick in some points, extra points, and then put some vectors there, and then repeat the whole thing. So the vector space is deforming its own structure. So see, that's what he showed. He showed that any element in the cohomology of the loop space satisfied the Moyer-Cartan equation, and so it created a deformation. So that the homology of the base loop space was, so to speak, deforming itself. It provided parameters for deformations of itself. And I'm wondering if these two things were connected. Siegel's idea and that.
Well, the space of states is the the space of states is actually the Hochschild homology, but there, if you have a certain duality. So in this setting, the Hochschild homology
duality, it's functions,
and the cohomology can be identified up to a shift, and so indeed, the space of states is actually also simultaneously controlling the deformation theory of A. If you
it seems to fit with Siegel's
yeah.
picture, huh?
Yeah, I guess so. This makes sense.